Hello, and welcome to Infinite Science. Before we begin, find somewhere quiet, somewhere you can sit still for a while, because what we're about to explore together demands something rare in our hurried world: patience. The kind of patience the universe itself practices. The kind of patience measured not in minutes or hours, but in millions and billions of years. Tonight, we're going to talk about stars, but not the stars you think you know, not the pinpricks of light poets write about, or the distant suns that decorate our night sky like scattered diamonds on black velvet, or the romantic symbols that appear in songs and stories and wishes. We're going to talk about what stars actually are, in the most literal, physical, scientific sense. What they actually do, how they work, how they live and die, and how profoundly, almost impossibly strange they really are when you understand them properly. Because stars are not what you think. They are not eternal flames burning in the heavens. They are not divine lights placed in the sky for our benefit or wonder. They are not simple balls of fire, not cosmic campfires, not celestial lanterns. They are machines, ancient, self-regulating billion-year machines that have been running since before Earth existed, before the sun ignited, before the first galaxy took shape in the cooling darkness after the Big Bang, before planets, before chemistry became complex enough for life, before time had any meaning to any conscious being anywhere in the universe. And they are still running now, right now, at this very moment. As you listen to these words, as you breathe, as your heart beats, as neurons fire in your brain. Somewhere out there, perhaps 60 trillion miles away, a distance so vast that light itself, traveling at 186,000 miles per second, takes years to cross it. A star is in the middle of its work. It has been doing this work, this same task, for 2 billion years. 2 billion years of continuous operation, without rest, without maintenance, without pause, without anyone watching or caring or knowing. It will continue for 2 billion more. It does not rest. It does not stop. It does not need to. It cannot stop, in fact, without collapsing. It simply burns, fuses, radiates, and creates, following the inexorable laws of physics, executing a program written into the fabric of reality itself at the moment of the Big Bang. This is not poetry, though it sounds like it. This is not metaphor or exaggeration or artistic license. This is physics. This is reality. This is what actually happens, what is happening right now, what has been happening for billions of years. And it is more beautiful, more profound, more awe-inspiring than any poem ever written. For most of human history, for nearly all of the 300,000 years our species has existed, for all but the last few centuries, we looked up at the stars and saw gods. We saw signs, omens, prophecies, stories written in fire across the dome of heaven. We saw purposes and meanings, destinies and fates written in light. The Babylonians 4,000 years ago in ancient Mesopotamia between the Tigris and Euphrates rivers mapped them with astonishing precision for their time, creating catalogues and star charts that tracked the movements of planets and the positions of constellations with accuracy that wouldn't be surpassed for over 1,000 years. Accuracy that allowed them to predict eclipses and planetary conjunctions, to create a calendar to mark the seasons. They saw the stars as manifestations of their gods, as divine beings whose movements determined human affairs, whose positions influenced fate and fortune. The Egyptians aligned their pyramids to them with architectural precision that still amazes us today. The Great Pyramid at Giza points to true north within 3.4 arc minutes, within a fraction of a degree, and its narrow shafts align with specific stars that were important to Egyptian cosmology: Sirius, Orion's belt, the North Celestial Pole. They saw the stars as the realm of the afterlife, as the destination of pharaohs and the blessed dead, as the eternal and unchanging heaven above the temporal and corruptible earth. The Polynesians navigated by them across thousands of miles of open Pacific Ocean, reading the sky like a map written in light, using the positions of stars rising and setting at different points on the horizon to find tiny islands, mere dots in the vast ocean. Atolls perhaps a mile across in an ocean thousands of miles wide, without any instruments, without compasses, without sextants, without chronometers, guided only by memory and traditional knowledge passed down orally through generations of navigators. They saw the stars as guides, as wayfinding companions, as the framework that made oceanic voyaging possible, that allowed them to settle every habitable island in the Pacific. Ancient shepherds in deserts from North Africa to Central Asia watched them wheel overhead through the long nights, noting which stars rose heliacally just before dawn, appearing briefly in the eastern sky before being washed out by the rising sun, to signal the coming of spring and the flooding of rivers like the Nile, to mark the proper time for planting crops. They saw the stars as seasonal markers, as cosmic calendars, as timekeepers for agriculture and herding, as practical tools for survival. Greek philosophers in the classical period debated their nature in torchlit academies in Athens and Alexandria and other centers of learning, arguing late into the night about the fundamental nature of reality. Were the stars holes in the celestial sphere through which divine fire shone from beyond the cosmos? Were they lamps hung by the gods for the benefit of humanity, to light the night and provide navigation? Were they living beings, perhaps divine or semi-divine entities, circling the earth in perfect crystalline spheres of increasing radius, making celestial music as they moved in their orbits, the music of the spheres that Pythagoras and his followers spoke of, an inaudible harmony arising from their perfect mathematical motions? Aristotle, perhaps the most influential philosopher of antiquity, taught that the stars were made of a fifth element, quintessence or ether, different from the four terrestrial elements of earth, water, air, and fire that made up everything on earth, and that they resided in the realm of the eternal and unchanging, the superlunary realm beyond the moon, fundamentally different from the corruptible and changing sublunary realm of earth. The heavens were perfect, eternal, divine. The earth was imperfect, temporary, mortal. That was the cosmic order, the great chain of being. This view, this cosmology, persisted for nearly 2,000 years, with remarkably little change. Through the Roman Empire, which adopted and adapted Greek astronomy and philosophy, incorporating it into their own worldview. Through the Middle Ages, when Islamic scholars in Baghdad and Damascus and Cordoba and other centers of the Islamic Golden Age preserved and advanced astronomical knowledge, making careful observations, building better instruments, calculating more accurate tables, while Europe languished in what we sometimes call the Dark Ages. Through the Renaissance, when European astronomers rediscovered ancient wisdom through translations from Arabic and Greek, and began to challenge it, to question it, to test it against observation. It wasn't until the late 16th and early 17th centuries that this picture began to crack, to fracture, to reveal its profound inadequacy in the face of new observations. Tycho Brahe, the Danish nobleman and astronomer famous for his golden prosthetic nose. He lost part of his real nose in a duel over a mathematical dispute when he was young, a reminder that even scholars could be violent. Observed a supernova in 1572, what he called a new star appearing suddenly in the constellation Cassiopeia, where none had been before, shining brightly enough to be visible in daylight for several weeks, then slowly fading over months. He measured its position carefully with his instruments and found no parallax, proving it was far beyond the moon, in the supposedly unchanging realm of the stars. He realized the heavens could change. The celestial realm was not immutable after all. Stars could appear. Perhaps they could also disappear. Perhaps the heavens were not so different from Earth. Giordano Bruno, the Italian philosopher and former Dominican friar, an original and often heretical thinker, speculated wildly and brilliantly that the stars were distant suns like our own, scattered through infinite space, each perhaps surrounded by its own planets like our solar system, perhaps with their own life, perhaps with their own intelligences looking up at their own skies and wondering. He suggested the universe was infinite in extent and had no center, that Earth was not special, that humanity was not the center of creation. He was burned at the stake in 1600 in Rome's Campo de' Fiori, executed by the Inquisition, though more for his theological heresies and rejection of Catholic doctrine, his denial of the Trinity, his views on the divinity of Christ, his mockery of transubstantiation, than for his astronomical speculations, though those didn't help his case with the authorities. Galileo Galilei, the Italian mathematician and natural philosopher, turned his telescope skyward in 1609, one of the first to do so for systematic astronomical observation, building on the invention by Dutch lensmakers, and saw wonders that shattered the old cosmology piece by piece. He saw mountains and craters on the moon, proving it was a world like Earth, rocky and rough, not a perfect crystalline sphere. He saw 4 moons orbiting Jupiter. We now call them the Galilean moons: Io, Europa, Ganymede, Callisto, proving not everything orbited Earth, that there could be other centers of motion. He saw the phases of Venus, waxing and waning like the moon through a full cycle, proving Venus orbited the Sun, not Earth, supporting the Copernican heliocentric model. He saw countless stars invisible to the naked eye when he pointed his telescope at the Milky Way, revealing that faint band of light to be composed of innumerable individual stars, too faint and distant to resolve without optical aid. The celestial sphere shattered under the weight of evidence. The perfect heavens crumbled. The idea that the heavens were fundamentally different from Earth, made of different elements governed by different laws, collapsed. The Earth was not the center of the universe. The stars were not holes in a sphere. The universe was vaster and stranger than anyone had imagined. But even then, even with the telescope and all these revolutionary discoveries, none of them, not one culture, not one civilization, not one philosopher or astronomer in all of human history up to that point understood what stars actually were, what they were made of, what kept them shining, how they worked. They knew stars were distant. They knew they were self-luminous, producing their own light rather than reflecting it like the moon. But that was about all. They saw light. We see machinery. They saw constancy and permanence. We see transformation and change, evolution and death. They saw eternity. We see deep time measured not in human generations or even in civilizational time spans, not in thousands or even millions of years, but in billions of years, in eons so vast that the entire span of recorded history, all 5,000 or 6,000 years of it from the first writing in Sumer to now, is less than a heartbeat in comparison, less than a fraction of a second in a cosmic day. It took us a very long time to understand this, longer than you might think, longer than seems reasonable given how bright stars are, how obvious their presence, how much they've fascinated humanity, how much effort we've put into studying them, even after Galileo and the telescope revolution of the 17th century. Even after Isaac Newton explained gravity in the Principia Mathematica in 1687 and showed that the same force that makes apples fall also keeps the moon in orbit and governs the motions of planets, unifying terrestrial and celestial physics. Even after we understood that our sun was itself a star, not a fundamentally different type of object, and that the stars were distant suns scattered across unimaginable reaches of space, a realization that came gradually through the work of astronomers like William Herschel, who mapped the structure of the Milky Way in the late 1700s and early 1800s with larger and larger telescopes, and Friedrich Bessel, who first measured stellar parallax in 1838, proving the stars were vastly distant, light years away, and thus must be enormously luminous to appear as bright as they do. Even after we measured the distances to nearby stars, light years, tens of light years, hundreds and thousands of light years, using parallax, the apparent shift in position due to Earth's orbit around the Sun, a tiny angular shift measured in fractions of an arcsecond, and later using other techniques like standard candles and spectroscopic parallax and Cepheid variables. Even after we analyzed starlight through spectroscopy in the mid-1800s, passing it through prisms and later diffraction gratings to spread the light into its component colors and reveal dark absorption lines, and discovered through careful analysis of those lines, through comparison with laboratory spectra of known elements, that stars were made of the same elements as Earth: hydrogen, helium, carbon, oxygen, iron, calcium, sodium, magnesium, and dozens of others, the same periodic table. We still didn't truly understand what kept them burning, what their energy source was. How could something burn for billions of years? What fuel could possibly last that long? What process could sustain such tremendous energy output over such vast timescales? The question haunted scientists throughout the 19th century. It was one of the great unsolved problems, one of the major challenges to physics and astronomy, one of the deepest mysteries of nature. For a while, starting around 1848, scientists thought the sun might simply be on fire, burning like coal or wood or oil, sustained by ordinary chemical combustion, by the oxidation of fuel. Julius Robert von Meyer, a German physician and physicist, proposed this. Hermann von Helmholtz and William Thomson, later Lord Kelvin, two of the leading physicists of the era, calculated carefully how long it would last, based on the energy released by chemical reactions. They assumed the best possible case: the sun made entirely of coal and oxygen, burning with perfect efficiency, converting all available chemical energy to heat and light with no losses. The answer came back: about 30,000 years. Maybe less, depending on assumptions about combustion efficiency. 30,000 years sounds like a long time to human intuition. To our limited perspective, it's longer than recorded history. It's longer than agriculture has existed. It's longer than cities. It's about as long as anatomically modern humans have been creating art and culture and symbolic thought. But geologists had already found rocks far older than that. Much, much older. Orders of magnitude older. James Hutton, in the late 1700s, the Scottish geologist often called the father of modern geology, and Charles Lyell in the 1830s, whose principles of geology influenced Darwin, had established the principle of uniformitarianism in geology. The idea that geological processes visible today operating at current rates, erosion, sedimentation, volcanism, uplift, could explain all of Earth's features given enough time. And the time required was immense, vastly greater than human history, vastly greater than the few thousand years allowed by biblical chronology based on adding up genealogies in Genesis. Fossils that required millions of years to form through slow processes of sedimentation, layer upon layer of sediment accumulating at rates of perhaps millimeters or centimeters per year, in river deltas and ocean basins, then compressing over time under the weight of overlying layers, then mineralizing as water percolated through and replaced original biological material with minerals. Marine sediments hundreds or thousands of meters thick in places like the White Cliffs of Dover or the Grand Canyon or the Gulf Coast, each thin layer representing years or decades or centuries of deposition, stacking up over incomprehensible spans of time, creating stratigraphic sequences that told stories of ancient seas and vanished mountains, visible in cliffs and canyon walls, and mountain faces where uplift and erosion had exposed them like pages in a book. The numbers didn't work. The timescales were incompatible, contradictory. The sun had to be far older than 30,000 years. The evidence from geology was overwhelming, undeniable. Then came another idea, more sophisticated, more grounded in physics, proposed independently by Lord Kelvin and Hermann von Helmholtz in the mid-1800s. Gravitational contraction, also called the Kelvin-Helmholtz mechanism. Perhaps the sun was slowly shrinking, slowly collapsing under its own weight at a rate too slow to detect, converting gravitational potential energy into heat and light as it contracted. Every meter the sun shrank would release energy according to the principles of Newtonian gravity and thermodynamics, energy that would heat the sun and radiate into space. This was better. This was based on solid, well-established physics, not speculation. This was grounded in Newton's laws, proven laws, and the laws of thermodynamics, which had been carefully worked out in the 19th century. Kelvin did the calculations carefully and thoroughly, accounting for energy loss through radiation and heat capacity and various efficiencies. This gave you maybe 15 to 20 million years, perhaps even longer with optimistic assumptions about the sun's initial state and structure. Possibly 30 million years. Possibly even 50 million if you pushed the assumptions. A respectable age by the standards of mid-19th century science, long enough for some significant geological processes, long enough for mountain ranges to erode, long enough for some evolution of life, still not enough, not even close to what the geologists were finding, not nearly enough for what Darwin's theory required. By the late 19th century, by the 1890s, geologists were finding evidence that Earth was hundreds of millions of years old, perhaps even approaching 1 billion years or more. The fossil record showed gradual evolution over vast timescales, layer upon layer of sediments containing different assemblages of fossils, showing a clear progression from simple to complex life forms. Charles Darwin's theory of evolution by natural selection, published in 1859 in On the Origin of Species, required enormous amounts of time for the diversity of life to develop through random variation and natural selection, through the slow accumulation of small changes over countless generations, through the patient work of descent with modification. Darwin himself estimated that the erosion of the Weald, a geological formation, a valley in southern England, had taken 300 million years based on the volume of material eroded and estimates of erosion rates, though this calculation was controversial and probably too high, but even conservative estimates required many tens of millions of years, possibly over 100 million. The erosion of mountain ranges like the Appalachians, worn down from peaks perhaps as high as the Himalayas to gentle, worn hills, over hundreds of millions of years. The deposition of sediments thousands of meters thick in places like the Grand Canyon, where you can see nearly 2 billion years of Earth history in the exposed rock layers, or the Gulf Coast, where sediments from the Mississippi have piled up kilometers thick. The formation of coal beds from ancient swamps and forests, compressed and heated over millions of years into the black rock we burn for fuel. The accumulation of chalk and limestone from the shells of countless tiny marine organisms, accumulating millimeter by millimeter on the ocean floor over tens of millions of years. All of these processes demanded timescales far, far beyond 20 or 30 or even 50 million years. Physicists, using the best available theories and careful calculations, the best physics of the 19th century, said it was impossible. The sun couldn't be that old. There was no known energy source sufficient to keep it shining for hundreds of millions of years, let alone billions. The laws of physics simply didn't allow it. Lord Kelvin, one of the most respected physicists of the 19th century, a founder of thermodynamics, a calculator of extraordinary skill, insisted on his results. He was certain. The physics was clear, the mathematics was rigorous. The sun was at most a few tens of millions of years old, probably less than 20 million. That was the limit. That was what physics said. Geologists and biologists insisted on their evidence with equal certainty. The rocks didn't lie. The fossils were real. The stratigraphic sequences were clear. The Earth was old. Very old, hundreds of millions of years old at minimum. Each discipline was confident in its methods, yet they gave contradictory answers to fundamental questions about the age of the Earth and Sun. It was a genuine crisis in science, a standoff, an impasse that couldn't be resolved within the existing framework of knowledge. Both sides had good reasons for their positions. Both were using the best methods available, yet they couldn't both be right. Something was missing. Some new physics, some unknown energy source, some principle not yet discovered, some fundamental aspect of nature that 19th century physics didn't account for, didn't know about, couldn't predict. The answer, when it finally came in the early 20th century, required a complete revolution in our understanding of matter, energy, space, time, and the fundamental forces of nature. It required overthrowing, or at least radically modifying, much of what was thought to be known. It required quantum mechanics, a framework that described nature at the atomic and subatomic scale. A theory that was strange and counterintuitive, and probabilistic rather than deterministic, developed over about 30 years by many contributors. Max Planck introduced the quantum of action in 1900, trying to solve the problem of blackbody radiation, and won the Nobel Prize in 1918. Niels Bohr developed the first quantum model of the atom in 1913, explaining atomic spectra and why atoms didn't collapse. Werner Heisenberg formulated matrix mechanics and the uncertainty principle in 1925. Erwin Schrödinger developed wave mechanics in 1926, giving us the Schrödinger equation that describes how quantum states evolve. And many others, Max Born, Paul Dirac, Wolfgang Pauli, Louis de Broglie, built the mathematical framework of quantum theory, a framework that worked brilliantly to predict experimental results despite being philosophically troubling. It required Einstein's special relativity, published in 1905, which united space and time into a single, four-dimensional space-time and showed that the speed of light was the same for all observers regardless of their motion, with profound implications for our understanding of simultaneity and causality and the nature of reality itself. And it required his famous equation E equals mc squared, also from 1905, derived in a follow-up paper to special relativity, showing that mass and energy were equivalent. Two forms of the same thing, interconvertible according to that simple, elegant formula that would change the world, though it took decades for people to fully realize the implications. It required understanding the atomic nucleus and the forces that hold it together, work done by Ernest Rutherford, the New Zealand-born physicist who discovered the nucleus in 1911 by bombarding gold foil with alpha particles and observing that some bounced back at large angles, implying a tiny, dense, positively charged core at the center of atoms rather than the plum pudding model that had been assumed. James Chadwick discovered the neutron in 1932, finally explaining what gave nuclei their mass. It wasn't just protons, which couldn't account for atomic masses, but protons and neutrons together. Hideki Yukawa proposed the strong nuclear force in 1935, mediated by mesons, particles that carried the force between nucleons, explaining how protons and neutrons bound together despite electromagnetic repulsion. And it required understanding nuclear fusion itself, work pioneered by Arthur Eddington in the 1920s, the British astrophysicist who first proposed seriously that stars might be powered by the conversion of hydrogen into helium, that the mass difference between 4 hydrogen atoms and 1 helium atom might provide the energy through E equals mc squared, that this could explain both the sun's luminosity and its longevity. Hans Bethe, a German-American physicist, worked out the detailed mechanisms in a famous 1939 paper, the proton-proton chain that powers stars like the sun, and the CNO cycle that powers hotter, more massive stars, calculating the reaction rates, the energy release per reaction, the temperature and pressure conditions required. He won the Nobel Prize in Physics in 1967 for this work, for explaining how stars shine, for solving one of the great mysteries of nature. The pieces came together slowly over decades of theoretical and experimental work. A new picture emerged through the combined efforts of hundreds of scientists, a revolution in astronomy and physics and our understanding of the universe. Stars don't burn chemically, converting fuel to ash through oxidation, through the rearrangement of electrons. They fuse atomic nuclei, converting hydrogen to helium, mass to energy, through nuclear reactions in their cores at temperatures of millions of degrees. That's the answer. That's the secret that eluded humanity for thousands of years. That's how stars work. And it's more remarkable than anyone could have imagined. Deep inside a star, in its core where the pressure is 200 billion times that of Earth's atmosphere at sea level, and the temperature reaches 15 million degrees Celsius. 15 million degrees, a temperature so extreme that there is nothing on Earth, nothing in human experience, nothing we can create even in our most advanced laboratories or nuclear weapons to compare it to, a temperature where matter behaves in ways completely alien to our intuition and everyday experience. Hydrogen atoms are crushed together with such tremendous force that they overcome the electromagnetic repulsion that normally keeps atomic nuclei apart. To truly understand how extraordinary this is, how unlikely, how delicately balanced, we need to understand the barrier, the obstacle that must be overcome. This electromagnetic repulsion is powerful, fundamental, universal. One of the basic forces of nature. It arises from Coulomb's law, one of the basic principles of electromagnetism discovered by Charles-Augustin de Coulomb in 1785 through careful experiments with charged spheres suspended on torsion balances, measuring the forces between them. 2 protons, both positively charged particles, each with a charge of +1 elementary charge, equal to about 1.6 times 10 to the power of -19 coulombs, naturally repel each other with electromagnetic force. Like charges repel, opposite charges attract. This is one of the first things you learn in physics, in chemistry, in any science class. It's fundamental to how matter behaves, to how atoms are structured, to chemistry and electricity and magnetism. The repulsive force between 2 protons follows an inverse square law, like gravity but much stronger at short ranges. It scales as the product of the charges divided by the distance squared. F equals kq 1q2 over r squared. As the particles get closer together, the force increases rapidly. At very small distances, at nuclear distances measured in femtometers, the repulsion becomes enormous, almost like hitting a brick wall made of pure force. Under normal conditions, at ordinary temperatures and pressures like those on Earth's surface or in its atmosphere or anywhere in everyday human experience, anywhere we live and work and exist, protons can never get close enough to touch, never get within range of the strong nuclear force that could bind them together. The electromagnetic barrier is too strong, too high. They approach each other, feel the repulsion getting stronger and stronger as they get closer, and bounce off, repelled, never merging. Even at extreme temperatures by human standards, temperatures in flames, thousands of degrees Kelvin where things glow red and yellow and white. Temperatures in Earth's core, perhaps 5,000 to 6,000 degrees, where iron is molten. Temperatures in lightning bolts, tens of thousands of degrees where air is ionized into plasma. It's nowhere near enough to overcome the barrier. The thermal energy, the kinetic energy particles gained from temperature, is far, far too small to punch through the electromagnetic repulsion between nuclei. To put some numbers on this, at 10,000 Kelvin, a typical proton has kinetic energy of about 1 electron volt. The electromagnetic barrier between two protons is about 500,000 electron volts. You're off by a factor of 500,000, not even close. To fuse hydrogen at any appreciable rate to overcome that barrier with any reasonable probability requires conditions utterly unlike anything on Earth, anything in everyday experience. It requires temperatures of millions of degrees, 10 million, 15 million, 20 million degrees, and densities hundreds of thousands of times higher than any solid, higher than lead, higher than gold, higher than any material we can make. But in the core of a star, in that hidden furnace at the center, buried under hundreds of thousands of kilometers of plasma, normal conditions do not apply. The rules are different. The environment is extreme beyond imagination, beyond anything we encounter in daily life, or can easily recreate in laboratories, though we're trying with fusion reactors. The temperature is so high, 15 million degrees Kelvin in the sun's core, even higher in more massive stars, 30 or 40 million degrees in the cores of massive stars, that hydrogen atoms have been stripped of their electrons entirely, torn apart by violent collisions. Electrons are ripped away by the sheer kinetic energy of thermal motion, by photons energetic enough to ionize atoms with single impacts. The core is not a gas in the ordinary sense, not like air or steam or any familiar substance, not with intact atoms bumping around like billiard balls. It is a plasma, the fourth state of matter after solid, liquid, and gas, a sea of naked atomic nuclei and free electrons, all moving at tremendous speeds, driven by temperature, colliding constantly with each other. Billions and billions of collisions per second for each particle. At 15 million degrees Kelvin, the average kinetic energy of a proton is about 2,000 electron volts, about 2 kilo electron volts in physics notation. That corresponds to a speed of several hundred kilometers per second, about 600 kilometers per second for a typical proton, about 0.2% of the speed of light. They're moving fast by human standards, faster than any bullet or rocket we've built. Smashing into each other with tremendous energy, far more energy than any chemical reaction could provide. Millions upon millions of collisions per second for each particle, creating a chaotic, turbulent maelstrom of particles and energy and radiation. The pressure is so intense, 200 billion times Earth's atmospheric pressure, hundreds of billions of atmospheres. Pressures we can barely achieve even momentarily in the most advanced compression experiments with powerful lasers focused on tiny targets or diamond anvil cells squeezing samples between gem-quality diamonds, that these nuclei are forced into close proximity despite their electromagnetic repulsion. They are squeezed together by the immense gravitational weight of the star pressing down from all directions, by the weight of layers upon layers upon layers of plasma, hundreds of thousands of kilometers deep, pressing down, compressing the core, creating pressures of millions or billions of tons per square centimeter, the mass of 100 Earths or more, pressing down on every cubic meter of core material. The density in the Sun's core is about 150 grams per cubic centimeter, about 150 times the density of water, more than 10 times denser than lead or gold or any metal, denser than any material found naturally on Earth's surface. For comparison, the densest element at room temperature is osmium at about 22.6 grams per cubic centimeter. The Sun's core is 7 times denser than that. The core is squeezed into a state that has no terrestrial equivalent, no familiar analog. And when nuclei, driven by thermal motion and compressed by gravitational pressure, get close enough, within about 1 femtometer, 1/1,000,000th of a billionth of a meter, 1/4,000,000,000th of a meter, closer than the size of a proton itself, which is about 1 femtometer in radius, distances where classical physics breaks down entirely and quantum mechanics takes over, where the wave nature of particles becomes critically important, where uncertainty principles matter. The strong nuclear force takes over and changes everything. The strong force is, as its name straightforwardly suggests, strong. Much stronger than electromagnetism at short ranges, about 100 times stronger at the femtometer distances where it operates. One of the 4 fundamental forces of nature, along with electromagnetism, gravity, and the weak nuclear force. But it only works at very short ranges, distances comparable to the size of an atomic nucleus. A few femtometers at most, maybe 3 or 4 femtometers maximum. Beyond a few femtometers, beyond the size of a small nucleus like helium or carbon, it drops off extremely rapidly, exponentially rather than as a power law, and has almost no effect. It falls to negligible strength within a distance of about 10 femtometers, about the size of a large nucleus like lead or uranium. It's like a kind of nuclear glue, incredibly powerful at binding nucleons, together but extremely short-ranged. Incredibly strong, stronger than any other force at short range, but only when things are almost touching at nuclear distances, only when you're already inside what would normally be considered the nucleus, already past the electromagnetic barrier. Within the nucleus, within that tiny realm measured in femtometers, millionths of billionths of meters, distances smaller than anything we can see even with the most powerful electron microscopes, smaller than any wavelength of light could resolve. It overwhelms electromagnetic repulsion completely and binds protons and neutrons together with incredible strength, holding the nucleus together against the electromagnetic force trying to blow it apart from all those positive charges repelling each other, creating stable configurations that can last billions or even trillions of years without decaying. So when protons are forced close enough together by the extreme conditions in a stellar core, by the combination of high temperature giving them enormous kinetic energy to approach each other, to partially overcome the electromagnetic barrier through sheer speed, and high pressure forcing them into proximity, increasing the density of particles to incredible levels, and thus the collision rate to astronomical numbers, the strong force can grab them and lock them together, binding them into a composite nucleus. They merge, they fuse, they become one nucleus instead of 2 separate ones. But even then, even with temperatures of 15 million degrees, providing 2,000 electron volts of kinetic energy, and pressures of hundreds of billions of atmospheres compressing the plasma to 150 grams per cubic centimeter. Even with all the power of a star's core concentrated at the center, most collisions still don't result in fusion. Not even close. Not even a tiny fraction. The electromagnetic barrier is still formidable, still a major obstacle, still far higher than the typical kinetic energy. Remember, 2,000 electron volts of kinetic energy versus a 500,000 electron volt barrier. You're still off by a factor of 250. Classical particles simply cannot overcome this barrier. They bounce off. Fusion only happens through quantum tunneling, a purely quantum mechanical phenomenon with no classical analog, no equivalent in everyday physics or Newtonian mechanics, where particles can, with some small probability, pass through energy barriers that classical physics says should be absolutely impenetrable, impossible to cross without sufficient energy. In quantum mechanics, particles aren't point objects moving along definite trajectories like billiard balls on a table. They're described by wave functions, mathematical functions in Hilbert space, that encode probabilities, clouds of possibility that describe where the particle might be found if you measure it. And wave functions, being waves, can extend beyond classical boundaries. They can penetrate into regions that should be forbidden classically, that shouldn't be accessible. They can exist partially on both sides of a barrier simultaneously, in a superposition of states. The wave function of a proton approaching the electromagnetic barrier doesn't just stop at the barrier and go to zero. It penetrates into the barrier, decaying exponentially with distance into the forbidden region, but not quite reaching zero. And if the barrier is thin enough, and at stellar core conditions the barrier is thin in quantum mechanical terms, there's a small but non-zero probability that the wave function extends all the way through to the other side. There's a small but non-zero probability that a proton can quantum tunnel through the electromagnetic barrier, can suddenly find itself on the other side without having enough energy to climb over classically, and suddenly find itself close enough for the strong force to bind it to another proton. This is fundamentally weird. It violates our intuitions about how things should behave. But it's real. It's been verified experimentally in countless ways. Quantum tunneling is essential to many technologies: scanning tunneling microscopes, tunnel diodes, flash memory in computers. It's how alpha decay works in radioactive nuclei. And it's absolutely essential for fusion in stars. Without quantum tunneling, stars couldn't exist. The sun couldn't shine. You couldn't be here. The probability of tunneling is very small for any individual collision between two protons. Tiny. Infinitesimal by human standards. The mathematical formula involves an exponential of an exponential, making it extraordinarily sensitive to energy and distance. At the typical energies in the Sun's core may be 1 collision in 10 to the power of 26, or 10 to the power of 28 results in fusion through tunneling. That's 1 in 100 million trillion, or 1 in 10 billion trillion. Most protons in the Sun's core will collide billions upon billions upon billions of times, trillions upon trillions of times, more collisions than there are stars in the observable universe, more collisions than you can meaningfully imagine, before finally undergoing fusion, before having that one extraordinarily lucky collision where quantum tunneling allows them to penetrate the barrier and fuse. A proton in the Sun's core has a typical lifetime before fusing of about 10 billion years, comparable to the total main sequence lifetime of the Sun. That's how long it takes on average, how many collisions are required, before the random chance of quantum tunneling finally succeeds for that particular proton. 10 billion years of collisions, trillions upon trillions of attempts, before success. 10 billion years of bouncing off other protons before finally merging with one. But, and this is crucial, there are so many protons in the core, so unimaginably many particles, that even with this incredibly low probability per collision, fusion happens constantly, continuously, every fraction of a second, billions upon billions of times per second throughout the core. The Sun's core contains about 10 to the power of 56 protons. That's 10 million trillion protons. A number so large it's almost meaningless to human intuition, utterly beyond what we can visualize or comprehend. If you tried to count them at 1 per second, it would take 10 to the power of 48 years, vastly longer than the current age of the universe. Each one of those protons is colliding billions of times per second with other protons, driven by thermal motion at hundreds of kilometers per second by the chaotic churning of the plasma. The total number of proton-proton collisions per second in the Sun's core is staggering, beyond comprehension, probably something like 10 to the power of 38 collisions per second throughout the entire core, maybe 10 to the power of 39. A number with 38 or 39 zeros after it. And even though only an infinitesimally small fraction of those collisions lead to fusion, maybe 1 in 10 to the 26th or 10 to the 28th, depending on the exact energy distribution, that tiny fraction of an incomprehensibly large number is still a very large number. About 10 to the power of 38 reactions per second in the Sun's core, protons successfully tunneling through the barrier and fusing, converting hydrogen to helium, mass to energy, sustaining the Sun's luminosity of 3.8 times 10 to the power of 26 watts. Through a complex series of reactions, the proton-proton chain in stars like the Sun and cooler stars, a multi-step process that builds up helium from hydrogen, or the CNO cycle in hotter, more massive stars, where carbon, nitrogen, and oxygen act as catalysts, 4 hydrogen nuclei, 4 single protons, are converted into one helium-4 nucleus containing 2 protons and 2 neutrons, bound together in a stable alpha particle configuration that will last essentially forever, that will never decay. That is one of the most stable nuclei in the universe. This is stellar nucleosynthesis, the term coined by Fred Hoyle in the 1950s, the creation of new atomic nuclei from lighter ones through nuclear reactions in stellar interiors, the process by which stars build up the periodic table, element by element, fusion by fusion, over billions of years of continuous operation. And in that transformation, in that conversion of 4 hydrogen nuclei into 1 helium nucleus, in that nuclear wedding where 4 become 1, something miraculous happens, something that Albert Einstein predicted and that powers every star in the universe and ultimately makes life possible. If you carefully measure the mass of 4 separate hydrogen-1 atoms and compare it to the mass of 1 helium-4 atom, using precision mass spectrometry with atomic mass units defined as exactly 1/12, the mass of a carbon-12 atom, carefully accounting for electrons and binding energies and relativistic corrections, you find that the helium weighs slightly less than the 4 hydrogens you started with. About 0.7% less, 0.7%, about 0.71% to be more precise with current measurements. 4 hydrogen atoms have a combined mass of about 4.032 atomic mass units. 1 helium atom has a mass of about 4.003 atomic mass units. The difference is about 0.029 atomic mass units per helium nucleus formed, which is about 0.7% of the initial mass, about 7 parts per thousand. That might not sound like much on first hearing. 0.7% seems small, negligible almost, a tiny fraction, barely noticeable. But we're talking about mass being converted directly to energy, not just released from chemical bonds. And mass, according to Einstein's special relativity, according to one of the deepest insights in 20th century physics, is equivalent to energy. They're the same thing, different forms of the same fundamental quantity, different aspects of a unified mass energy. Where did the missing mass go? What happened to those 0.029 atomic mass units? Did it disappear into nothingness? No. It didn't disappear. Mass energy is conserved. That's a fundamental law of physics, perhaps the most fundamental law. The mass converted into energy, transformed, changed form, but didn't vanish. Matter became radiation. Substance became light and kinetic energy and momentum. Pure energy in accordance with the most famous equation in all of physics. Perhaps the most famous equation ever written by any human being. Certainly the most culturally recognized equation in the world. E equals mc squared. Energy equals mass times the speed of light squared. 3 symbols, 3 variables. 1 equals sign. Profound simplicity hiding revolutionary implications. Einstein published this equation in 1905 in a 3-page follow-up paper to his special theory of relativity, a paper titled in German, Ist die Trägheit eines Körpers von seinem Energieinhalt abhängig? Which translates to, does the inertia of a body depend upon its energy content? The answer, Einstein showed through careful reasoning about the emission of light from moving bodies, was yes. Emphatically, yes. Mass and energy are interchangeable. It tells us that mass and energy are the same thing, seen from different perspectives, 2 aspects of the same underlying physical reality, 2 faces of the same coin, 2 ways of describing the same quantity in nature. 2 columns in the ledger book of the universe that must always balance. Mass can convert to energy through processes like fusion, where nuclei combine and lose mass, or through matter-antimatter annihilation, where particles meet their antiparticles, and both vanish in a flash of gamma rays. Energy can convert to mass through pair production, creating electron-positron pairs from gamma rays in strong fields, or through any high-energy collision where kinetic energy becomes new particles. They are equivalent, unified, related by the speed of light squared, interchangeable under the right circumstances. And because c, the speed of light in vacuum, is a very large number, about 300 million meters per second, exactly 299,792,458 meters per second by definition in modern physics, where we define the meter in terms of CIE. And because we square it, making it about 9 times 10 to the power of 16 meters. Squared per second squared, even a tiny amount of mass converts into a staggering, almost incomprehensible amount of energy. The speed of light squared is an enormous conversion factor, one of the largest numbers in physics, with direct physical meaning. It means that a little mass equals a lot of energy, an enormous amount of energy. More energy than you can easily comprehend. Let's put some concrete numbers on this to make it real, to give it human scale, to understand what this actually means in practice for stars and for the universe. 1 kilogram of hydrogen, 1 single kilogram, fully fused into helium with perfect efficiency through complete conversion of 4 hydrogens to 1 helium. No losses to neutrinos or radiation. Complete conversion of that 0.7% mass difference into usable energy releases about 90 petajoules of energy. 90 petajoules. That's 90,000 trillion joules. 9 times 10 to the power of 16 joules. 9 followed by 16 zeros. A number so large it defies intuition. So large we need comparisons and analogies to understand it. To put that in human perspective, to give it scale we can grasp, that's as much energy as burning about 3 million kilograms of coal, assuming typical coal with energy content of about 30 megajoules per kilogram, about 8.3 kilowatt hours per kilogram. 3,000 metric tons of coal, 3 million kilograms. The entire contents of a large freight train of coal cars, a train perhaps a kilometre or more long, 100 cars, each loaded with 30 tons. Or detonating about 20,000 tons of TNT, 20 kilotons explosive yield. The explosive power of the atomic bomb, codenamed Fat Man, that was dropped on Nagasaki, Japan on August 9th, 1945. 3 days after Hiroshima, which killed about 40,000 to 75,000 people immediately in the blast and firestorm, and radiation, and caused tens of thousands of additional deaths from radiation sickness and injuries and cancer over the following months and years and decades, and destroyed much of the city, flattening buildings and igniting fires across square kilometers. From 1 kilogram of hydrogen, just 1 kilogram, a liter of liquid hydrogen if you could somehow collect and compress it, though hydrogen is hard to liquefy. The mass of a large textbook or a liter of water, the amount of hydrogen in about 10 liters of ordinary water, since water is H2O, 2 hydrogens per molecule. Let that sink in for a moment. Really contemplate it. Visualize it if you can, though it's difficult. 1 kilogram of fuel producing as much energy as 3 million kilograms of chemical fuel being burned, or as much as a nuclear weapon that destroyed a city and killed tens of thousands of people. A 3 million to 1 energy density ratio compared to chemical combustion. 1 million times more energy per kilogram than gasoline or diesel fuel or any hydrocarbon. 1,000 times more energy per kilogram than the most powerful chemical explosives like TNT or RDX or PETN. This is why fusion is so powerful compared to anything chemical. This is why nuclear energy, whether fusion like in stars or fission like in power plants and weapons, dwarfs chemical energy, makes it look puny by comparison. It taps into the strong force, the most powerful force in nature at short range, rather than just the electromagnetic force between electrons rearranging in chemical reactions. It converts mass directly to energy via E equals mc squared, rather than just rearranging electron configurations and releasing the energy difference between chemical bonds. This is the power of E equals mc squared. This is the power of mass energy equivalence. This is what nuclear forces can do when you allow nuclear transformations. This is what stars do, what they've been doing for billions of years since they first formed, what they'll continue doing for billions or trillions of years more until their fuel runs out. They are fusion reactors, the most powerful sustained energy sources in the universe, operating at a scale and duration that dwarfs anything humanity has ever built, or imagined building, or likely will build in the foreseeable future, operating without maintenance or refueling, self-regulating through negative feedback, stable for eons, reliable beyond any human technology. The sun converts 600 million tons of hydrogen into helium every single second. Every second of every day of every year for billions of years, without pause, without rest, without stopping, without anyone operating it or maintaining it. 600 million metric tons per second, 600 billion kilograms per second. The mass of a large mountain range, like a significant chunk of the Rockies or the Alps or the Himalayas, converted from hydrogen to helium, transformed element by element, every single second. Think about that number for a moment. Try to visualize it, though it's almost impossible to truly comprehend. 600 million tons, every second. Second after second after second, 60 times per minute, 3,600 times per hour, 86,400 times per day, 31.5 million times per year. And it's been happening for 4.5 billion years. 4 million tons of that mass, 4 million tons every second, about 4 times 10 to the power of 9 kilograms per second, about 4 times 10 to the power of 12 grams per second, is converted directly into energy according to Einstein's equation, according to E equals mc squared. It ceases to be matter, ceases to have mass. It becomes pure energy, pure radiation, photons carrying electromagnetic energy and neutrinos carrying weak force energy. 4 million tons of matter converted to energy, annihilated in a sense though not through antimatter, transformed from one form to another every second for 4.5 billion years so far, and for another 5 billion years to come before the hydrogen runs out. Do the arithmetic and the numbers become almost incomprehensibly large, straining the limits of what we can meaningfully grasp. 4 billion tons per second times 31.5 million seconds per year gives about 1.26 times 10 to the power of 17 tons per year, or 1.26 times 10 to the power of 20 kilograms per year. Over 4.5 billion years, that's about 5.7 times 10 to the power of 29 kilograms of mass, converted from hydrogen to helium. For comparison, Earth's entire mass is about 6 times 10 to the power of 24 kilograms. The Sun has converted the equivalent of about 100,000 Earth masses of hydrogen to helium over its lifetime. Not 100,000 Earths total. The Sun is about 330,000 Earth masses, but 100,000 Earth masses worth of hydrogen transformed, and it still has enough fuel for another 5 billion years at the current rate. The Sun is only about halfway through its hydrogen supply in the core, about halfway through its main sequence lifetime. The energy generated appears initially in two forms: gamma-ray photons, high energy, electromagnetic radiation produced directly by the nuclear reactions, each photon carrying millions of electron volts of energy, enough to ionize thousands of atoms or break molecular bonds or cause radiation damage to DNA. And neutrinos, ghostly, nearly massless particles, fundamental particles with almost no interaction with matter, that carry away about 2% of the energy and escape the Sun almost immediately, within seconds of being produced, passing through hundreds of thousands of kilometers of dense plasma as if it were vacuum, traveling at nearly the speed of light. The neutrinos are fascinating particles, well worth a brief digression. About 2% of the Sun's total luminosity, about 2% of that 3.8 times 10 to the 26th power watts, is in the form of neutrinos rather than photons. They're produced in the weak force reactions that convert protons to neutrons as part of the fusion chain, and they escape immediately because they interact so weakly with matter. The weak nuclear force is, as its name suggests, weak, and neutrinos have no charge and almost no mass, making them almost ghost-like. Trillions of solar neutrinos pass through your body every second coming from the Sun. About 65 billion neutrinos per square centimeter per second at Earth's distance from the Sun. They pass through the entire Earth without interacting, without being stopped or absorbed. You could build a wall of lead a light year thick, and most neutrinos would pass through without hitting anything. Detecting solar neutrinos was one of the great experimental challenges of 20th century physics. It required building massive detectors deep underground to shield from cosmic rays, tanks containing hundreds of tons of carefully purified chlorine or water or gallium, and waiting for months or years to catch a handful of neutrinos interacting with nuclei. The first successful detection came in the 1960s with Raymond Davis's chlorine detector in the Homestake mine in South Dakota, a gold mine repurposed for physics using a tank containing 100,000 gallons of perchloroethylene, dry cleaning fluid. It detected only about 1/3 of the predicted neutrino flux, creating the famous solar neutrino problem that puzzled physicists for decades until it was resolved. The resolution came in the 1990s and 2000s through experiments in Japan, Super Kamiokande, and Canada, Sudbury Neutrino Observatory. Neutrinos oscillate between three types: electron neutrinos, muon neutrinos, tau neutrinos, as they travel through space. The detectors were only sensitive to electron neutrinos produced in the Sun, but by the time they reached Earth, some had converted to the other types. When all types were counted properly, the flux matched theoretical predictions almost perfectly. This was confirmation, direct experimental proof that the proton-proton chain was really happening in the sun's core exactly as theory predicted, that fusion was really powering the sun, that our theoretical understanding was correct. The neutrinos are messengers from the core, arriving within seconds of being produced, carrying direct information about nuclear reactions happening right now in the sun's center. The gamma rays, unlike the neutrinos, cannot escape immediately. They're absorbed almost instantly within micrometers of where they're produced. They begin a long, tortuous journey outward through the sun's interior, bouncing from atom to atom, scattering randomly off free electrons and nuclei in the plasma, gradually losing energy and increasing in wavelength with each interaction, degrading from gamma rays to X-rays, to ultraviolet, to visible light, to infrared through a process called thermalization. This journey from core to surface, this random walk through the dense plasma of the solar interior where the opacity is high and photons can only travel tiny distances before scattering, takes an incredibly, almost unbelievably long time. Not minutes, not hours, not days or years. Thousands of years. Perhaps hundreds of thousands of years. Estimates vary from about 50,000 years to 1,000,000 years, or even more depending on modeling assumptions about the sun's interior structure, opacity, convection, and the exact path photons take. The calculation is complicated because photons don't travel in straight lines. They random walk, taking a meandering path that's much longer than the direct distance. If you calculate the average distance a photon travels between scatterings, the mean free path, it's perhaps a centimeter in the dense core. A photon travels a centimeter, scatters, changes direction, travels another centimeter in a random direction, scatters again, over and over, billions of times, slowly working its way outward through sheer random chance. The mathematical treatment is a diffusion equation, similar to heat conduction or the spread of perfume in a room. The time for diffusion to carry energy from center to surface goes as the square of the distance, so even though the sun is only about 700,000 kilometers in radius, the photons might travel a total effective distance of many light years, due to all the scattering, covering that distance at less than the speed of light, due to constant absorption and re-emission. The photons random walk outward, taking a drunkard's walk, a Brownian motion path, scattering billions or even trillions of times, each time changing direction essentially randomly, slowly diffusing toward lower density regions where scattering is less frequent, eventually reaching the photosphere where the density drops low enough that photons can escape into space. By the time they emerge from the sun's photosphere, the visible surface, though the sun has no solid surface, just a region where the plasma becomes optically thin, where the density drops enough that photons can travel freely without being absorbed, they have been completely thermalized, degraded from high-energy gamma rays carrying millions of electron volts, to a thermal distribution of photons with a black-body spectrum corresponding to the photosphere's temperature of about 5,800 Kelvin. The light we see, the sunlight that warms Earth and powers photosynthesis and makes life possible, left the sun's visible surface about 8 minutes and 20 seconds ago. That's how long it takes for light to travel the 150 million kilometers, 1 astronomical unit, from sun to Earth at 300,000 kilometers per second. But the photons themselves, the actual photons entering your eye when you look at the sky or hitting a solar panel, or being absorbed by a leaf, were produced as gamma rays in nuclear fusion reactions in the sun's core perhaps 100,000 years ago. Give or take a factor of several, depending on the exact path they happen to take through the random walk. During the last ice age, roughly, when mammoths and woolly rhinoceroses roamed across northern continents, and saber-toothed cats hunted in the Americas and Neanderthals still existed in Europe, and our ancestors were hunter-gatherers living in small bands, when there were perhaps only a few million humans on the entire planet, before agriculture, before cities, before writing, before civilization. The light reaching you now is ancient, older than recorded history, older than farming, older than permanent settlements, produced when our species and our world were very different. You are seeing ancient light, light that has been traveling, diffusing, random walking through plasma and then streaming through vacuum for 100,000 years plus 8 minutes. Light older than the pyramids, older than Stonehenge, older than any human monument or artifact, carrying energy from nuclear reactions that happened when your ancestors were an archaic form of Homo sapiens, or possibly even still Homo heidelbergensis, depending on the exact timing. And the sun has enough fuel, enough hydrogen remaining in its core and in the surrounding convective envelope that will eventually mix down into the fusion region. To continue doing this, to continue this process of fusion and energy generation for another 5 billion years, give or take perhaps 500 million depending on exact models and mass loss rates. 5 billion years of continuous operation ahead of it. 5 billion years of continuous fusion. 5 billion years of converting 4 million tons of mass to energy every single second, of producing 3.8 times 10 to the power of 26 watts of power, of radiating light across the solar system and beyond into interstellar space. 5 billion years. Try to comprehend that duration. Try to imagine it. All of human civilization, all 10,000 years of it from the first agriculture to now, is 0.0002% of 5 billion years. A fifth of 1,000th of 1%, essentially zero on that timescale. All of human existence as a species, perhaps 300,000 years, is 0.006% of 5 billion years, 6,000ths of 1%. A rounding error, the age of complex life on Earth, perhaps. 600 million years since the Cambrian explosion is 12% of 5 billion years. A decent fraction, but still much less than the future lifetime remaining to the Sun. The Sun has already lived for 4.5 billion years, and will live for perhaps another 5 billion, for a total main sequence lifetime of about 9 to 10 billion years, depending on exact models. This is not a fire in any ordinary sense, not combustion in the chemical sense, not anything like familiar flames. Chemical combustion, the burning of wood or coal or gasoline or natural gas or any chemical fuel, the flames in your fireplace or stove or car engine, involves rearranging electrons, breaking old chemical bonds between atoms and forming new ones, rearranging the electron clouds around atomic nuclei while leaving the nuclei themselves completely unchanged. The energy released comes from electromagnetic forces between electrons, from the difference in electromagnetic potential energy between reactants and products, from the rearrangement of electron configurations into more stable, lower energy states. When carbon reacts with oxygen to form carbon dioxide, for example, or when hydrogen reacts with oxygen to form water, or when methane burns, the electrons rearrange into more stable configurations around the same nuclei, lower energy states, and the difference in energy is released as heat and light, as thermal radiation and kinetic energy of product molecules. That's combustion, that's oxidation, that's fire. That's what happens in every familiar flame. The nuclei don't change. Carbon stays carbon. Oxygen stays oxygen. Hydrogen stays hydrogen. You're just rearranging which atoms are bonded to which other atoms, which electrons are shared in which molecular orbitals. Nuclear fusion involves rearranging the nucleus itself, not just the electrons around it, binding protons and neutrons together in new configurations, actually changing what elements are present at the nuclear level, transforming hydrogen nuclei into helium nuclei, one element into a completely different element. Transmutation, alchemy made real through physics rather than mysticism. The energy released comes from the strong nuclear force, not the electromagnetic force between electrons. From the conversion of mass to energy via E equals mc squared, not just from rearranging electron configurations. From the incredible binding energies that hold nuclei together against electromagnetic repulsion, energies far larger than chemical bond energies. About 1,000,000 times more powerful per reaction in terms of energy released per nucleus transformed compared to chemical reactions per molecule. About 1,000,000 times more energy per kilogram of fuel when you compare fusion of hydrogen to combustion of hydrocarbons, gram for gram, reaction for reaction. This is why nuclear energy, whether fusion like in stars or fission like in nuclear power plants, is so much more potent, so much more concentrated, so much more powerful per unit mass than chemical energy. It taps into the strong force, the most powerful force in nature at short range, the force that binds quarks into protons and neutrons and binds nucleons into nuclei, rather than just the electromagnetic force between electrons. It converts mass directly to energy via Einstein's most famous equation, rather than just rearranging electron shells. This is a controlled, ongoing thermonuclear reaction, more controlled and stable than any fusion reactor humans have built, or likely will build for decades to come. Despite enormous efforts stabilized by automatic negative feedback mechanisms built into the physics, by the interplay of gravity and pressure, held in perfect balance for billions of years through processes that require no intelligence or design or intervention. A billion-year machine running continuously without maintenance, without refueling, without operators, without computers or control systems, self-regulating through the laws of physics, self-stabilizing through thermodynamics. That's what a star is. That's what the sun is. That's what every point of light you see at night is, though they differ in details. And it's been doing this for 4.5 billion years, since it condensed from a molecular cloud and ignited fusion in its core. It will continue for another 5 billion years until the hydrogen in its core is exhausted. And then, as we'll explore, it will change, evolve, transform into something different, beginning a new chapter in its existence. But for now, for these 10 billion years of main sequence life, it simply fuses hydrogen, converts mass to energy, and shines. The stars are not what you think. They are not eternal flames, not divine lights, not simple fires. They are machines, self-regulating fusion reactors, engines of nuclear synthesis, billion-year engines running on quantum mechanics and gravity, and they are still running, right now, as you read these words. Across the galaxy, across the universe, in this moment, stars are fusing hydrogen into helium, converting mass to energy, radiating light into space. Some of those stars are young, just ignited, beginning their billion-year journey. Others are old, approaching the end, their cores filling with helium ash, their hydrogen depleting. Some are dying, swelling into red giants, shedding their outer layers. Some are exploding, scattering their contents across light years. The work continues. The machines run. The universe builds complexity from simplicity, one atom at a time, one fusion reaction at a time, one star at a time. And you are made of the products of these machines. Every atom in your body except the primordial hydrogen was forged in stellar cores or supernova explosions. You are stardust, literally, not metaphorically. The carbon in your DNA, the oxygen you breathe, the calcium in your bones, the iron in your blood, all forged in stars, all created by fusion reactions or supernova, nucleosynthesis, all scattered into space when stars died, all gathered by gravity into new clouds, new stars, new planets, all eventually assembled through billions of years of cosmic evolution into you. Look up tonight, see the lights in the sky, understand what you're seeing. You're seeing machines, fusion reactors, element factories, the forges that made you, the engines still working, still creating, still transforming hydrogen into complexity. The stars are still burning, the work continues, and you are here to witness it. Here is the fundamental tension, the central paradox that governs every moment of a star's existence. Gravity wants to crush it, to compress it into the smallest possible volume, to collapse it into a point, to release all its gravitational potential energy at once. Fusion wants to blow it apart. The tremendous pressure from gamma-ray photons, from the thermal motion of plasma at millions of degrees, pushes outward with enough force to overcome the weight of hundreds of thousands of kilometers of overlying material. And between these two opposing forces, in the narrow regime where they exactly balance, where inward pull perfectly equals outward push, a star finds equilibrium and lives its life. This balance is called hydrostatic equilibrium. It's the fundamental condition for stellar stability, encoded in the equations of stellar structure, first worked out in detail in the early 20th century by Arthur Eddington and others. At every point inside the star, at every radius from the center to the surface, the inward gravitational force per unit volume must exactly equal the outward pressure gradient. If they don't balance, the star either contracts or expands until they do. It's a delicate balance, a knife edge, a tightrope. But stars don't fall off that tightrope easily. They're remarkably stable, and the reason is negative feedback, automatic self-regulation built into the physics. If the core temperature increases, even slightly, fusion reactions accelerate dramatically because reaction rates are extremely temperature sensitive, scaling as temperature to the 4th or even 15th power depending on which reactions dominate. More energy is produced. Pressure increases. The core expands. As it expands, density decreases because the same mass occupies a larger volume. As density decreases, particles are farther apart, collision rates drop. Temperature falls slightly due to the expansion. Fusion slows back down. The star automatically corrects itself, returning to equilibrium without any external intervention. If the core cools slightly, the opposite happens. Fusion slows. Less energy is produced. Pressure decreases. The core contracts under the weight of overlying layers. As it contracts, density increases. Particles are squeezed closer together. Temperature rises due to compression, due to gravitational energy being converted to thermal energy according to the virial theorem. Fusion speeds up. Again, automatic correction. Return to equilibrium. This negative feedback, this thermostat effect, is why stars can remain stable for billions of years, why they don't wildly oscillate or explode or collapse, why they're so reliable. The star regulates itself. No intelligence required, no control systems, no computers or sensors or actuators, just physics, just thermodynamics and gravity and nuclear reaction rates, all coupled together in a self-stabilizing system. A machine that tunes itself automatically and maintains itself in perfect balance for eons. Our sun has been doing this for 4.5 billion years, every moment of every day, automatically maintaining hydrostatic equilibrium, automatically balancing gravity against fusion pressure. It will continue for another 5 billion years until something fundamental changes, until the fuel begins to run out. But that's far in the future. For now, The sun is stable, middle-aged, in the prime of its life. And so are most of the stars you see in the night sky. Most visible stars are on the main sequence, fusing hydrogen in their cores, in stable equilibrium, doing exactly what the sun is doing. But not all stars are the same. Not all stars burn at the same rate or live the same lifespan. Mass determines everything. Stars come in a remarkable variety, from the smallest to the largest, from red dwarfs barely able to sustain fusion to blue supergiants shining with the power of millions of suns. And mass is destiny. The mass of a star, how much material it managed to accumulate during formation, determines almost everything about its life. Its temperature, its luminosity, its color, its size, its lifespan, what elements it will create, how it will die. Mass determines all of these things through the physics of stellar structure. The smallest stars capable of sustaining hydrogen fusion are red dwarfs, with masses between about 0.08 and 0.4 solar masses, between 8% and 40% of the sun's mass. These stars burn slowly, incredibly slowly, economically, efficiently. Their cores are relatively cool by stellar standards, perhaps 8 or 9 million degrees, compared to 15 million for the sun. The fusion reactions proceed at a glacial pace. They sip their fuel carefully, like a car in extreme economy mode, extracting every possible joule from every hydrogen atom. The energy output is tiny by stellar standards. A typical red dwarf might be only 1/10,000th as luminous as the sun. Some are even dimmer, 100,000th as bright, or 1/1,000,000th. If you replace the sun with a typical red dwarf, Earth would freeze solid within weeks. The oceans would ice over kilometers thick. The atmosphere would condense and fall as snow, first water vapor, then carbon dioxide, then eventually even nitrogen and oxygen. The surface temperature would plummet to perhaps 50 or 70 Kelvin, colder than the coldest place in the solar system, colder than Pluto. All life would die, not just humans, everything. Even the most extreme thermophiles, the heat-loving bacteria that live in volcanic vents at 122 degrees Celsius, couldn't survive. You couldn't see most red dwarfs with the naked eye, even if one were nearby, say 5 or 10 light years away. They're too faint, too dim. Their light is too red, too far toward the infrared, too weak to stimulate our retinas effectively. Our eyes evolved to see sunlight, to be most sensitive to yellow-green light around 550 nanometers wavelength, the peak of the sun's spectrum. Red and infrared light, especially the deep red of cool stars, barely registers. Proxima Centauri, the closest star to our solar system at just 4.24 light-years away, our nearest stellar neighbor closer than any other star, is a red dwarf. You can't see it without a telescope despite being so close. It's magnitude 11, far below naked eye visibility, which stops around magnitude 6 under dark skies. You need binoculars at minimum, preferably a telescope. But what red dwarfs lack in brightness, they make up for in longevity, in endurance, in sheer persistence across cosmic time. A red dwarf with 10% of the sun's mass can fuse hydrogen for 10 trillion years. 10 trillion, 10,000 billion, 10 million million. To put that in perspective, the universe is currently 13.8 billion years old. 10 trillion years is more than 700 times the current age of the universe. Some calculations suggest the smallest, most efficient red dwarfs, those that fully convect, circulating their entire mass and continuously bringing fresh hydrogen to the core, could last even longer. 20 trillion years, 30 trillion, possibly even longer, long after the sun has died and cooled to a black dwarf. long after every bright star visible in Earth's current night sky, Sirius, Vega, Rigel, Betelgeuse, Arcturus, all of them, has exhausted its fuel and either faded to a white dwarf or exploded as a supernova. Long after the Milky Way and Andromeda galaxies have collided and merged sometime in the next few billion years, their spiral arms destroyed, their gas mixed and redistributed, combining into a single giant elliptical galaxy that astronomers have already nicknamed Milkomeda. Long after star formation has slowed to a trickle and nearly ceased as the universe expands and gas becomes too diffuse to collapse into new stars, as most of the hydrogen gets locked up in stars or brown dwarfs or expelled from galaxies. Long after the universe has grown cold and dark and sparse, filled mostly with the slowly cooling remnants of dead stars, red dwarfs will still be burning, still fusing hydrogen, still radiating their feeble red glow into an increasingly empty cosmos. They will be the last lights in the universe, the final embers, the last stars shining in the gathering darkness. When the last red dwarf finally exhausts its fuel and fades, tens of trillions of years from now, the age of stars will truly be over. The universe will enter the so-called black hole era, lit only by the faint glow of cooling stellar remnants and the even fainter Hawking radiation from slowly evaporating black holes. But that is so far in the future, such an incomprehensible timescale that it borders on the meaningless for any human understanding. For now, for the next trillion years at least, red dwarfs will keep burning, patient, economical, persistent. At the opposite extreme are the massive stars, the blue giants and supergiants, the stellar leviathans, stars with 20, 50, 100, even 200 times the mass of the Sun. Some of the most massive stars known, stars like R1, 36, or 1 in the Tarantula Nebula, or stars in the Arches cluster near the galactic center, may exceed 200 or even 250 solar masses, though there's some uncertainty about exact masses. There's probably an upper limit to stellar mass, somewhere around 200 to 300 solar masses, set by the Eddington limit, where radiation pressure becomes so strong it blows away infalling material and prevents the star from accreting more mass during formation. These massive stars burn fast, furiously, violently, extravagantly, profligately. Their cores are tremendously hot, not 15 million degrees like the Sun, but 30 million, 40 million, 50 million degrees, or even higher. The most massive stars might have core temperatures approaching 100 million degrees during their main sequence lives. At these extreme temperatures, fusion proceeds at a ferocious rate. Remember that reaction rates are extremely temperature sensitive. For the CNO cycle that dominates in massive stars, the reaction rate scales as something like temperature to the 15th or even 20th power. A small increase in temperature produces an enormous increase in reaction rate. Double the temperature, and the reaction rate might increase by a factor of 30,000 or more. The energy output is staggering, incomprehensible, almost unbelievable. A blue supergiant can be 1,000,000 times more luminous than the Sun. The most luminous stars known are perhaps 8 or 9 million times more luminous. R136, one of the most massive and luminous stars known, is about 8.7 million times more luminous than the Sun. Let me repeat that, 8.7 million times brighter. The Sun radiates 3.8 times 10 to the power of 26 watts. R136, a 1 radiates about 3.3 times 10 to the power of 33 watts. That's 3.3 billion trillion watts. More power than a billion suns combined. If you placed R136, A1 where the Sun is, at 1 astronomical unit from Earth, The planet would be vaporized in a fraction of a second, not gradually, instantly. The surface of Earth would be heated to tens of thousands of degrees, Kelvin in milliseconds. The rocks would vaporize, turn directly to gas, subliming and then dissociating and ionizing. The entire planet would become a rapidly expanding cloud of plasma, silicon and iron and oxygen ions, glowing white-hot, then be blown away by radiation pressure and the stellar wind, which would be moving at thousands of kilometers per second. Nothing solid could exist anywhere near such a star. The habitable zone, if you could call it that, would be hundreds or thousands of astronomical units away, far beyond Pluto's orbit. The radiation, the stellar wind, the sheer energy output would sterilize space for light years in all directions. But massive stars are brief, ephemeral by cosmic standards, mayflies compared to red dwarfs. They burn through their fuel with reckless abandon, consuming their hydrogen reserves at prodigious rates. A star like Rigel, the bright blue-white star marking Orion's foot, is perhaps 20 times the Sun's mass. It's perhaps 8 to 10 million years old. It will die in another 2 or 3 million years. Total main sequence lifetime, perhaps 10 to 12 million years, maybe less. Compare that to the Sun's 10 billion years. Rigel lives 1,000 times faster and dies 1,000 times younger. Or consider an even more massive star, perhaps 50 or 100 solar masses. These monsters might last only a few million years. 2 million, 3 million. They're born, they live fast, they die young, all in less time than it took for humans to evolve from our Australopithecine ancestors. By cosmic standards, massive stars barely exist. They flare up and disappear in an eye blink. And then there's everything in between these extremes. A continuum of stellar types, a spectrum of masses and properties. Yellow stars like our Sun, G-type main sequence stars. The Sun is about 4.6 billion years old and will live to about 10 billion years total. Middle-aged, middle mass, middle of the road in almost every way. Orange stars, K-type stars, cooler and dimmer than the Sun. They might live 15 or 20 billion years, longer than the current age of the universe. White stars, A-type and F-type stars, hotter and brighter than the Sun. They might live only 1 or 2 billion years, burning faster, dying younger. Each star is a machine calibrated to its own mass, running on its own timescale, following its own evolutionary path determined primarily by that one number, its mass in solar units. The universe is full of them, hundreds of billions in our galaxy alone, perhaps 200 billion, perhaps 400 billion. The exact number is uncertain because many stars, especially the faint red dwarfs, are hard to detect, and parts of the galaxy are obscured by dust. And 2 trillion galaxies in the observable universe, each with hundreds of billions of stars on average. Do the math. Roughly 400 sextillion stars. 4 times 10 to the power of 23 stars. 400,000 billion stars in the visible universe, each one a fusion reactor, each one converting mass to energy, each one following the program encoded in physics, each one running until its fuel is exhausted. For most of a star's life, for the vast majority of its existence, nothing dramatic happens. This bears repeating because it's so important to understanding stars. A star on the main sequence is stable, predictable, boring by cosmic standards. If you watched a sun-like star for 1 billion years, a period utterly beyond human comprehension, you would see almost no change. The same brightness within a few percent, the same color, the same size, the same spectrum. It rises, crosses the sky, sets, day after day, year after year, century after century. millennium after millennium, eon after eon, for millions of years, billions of years. The same processes repeating endlessly. Hydrogen fusing to helium in the core, energy diffusing outward through the star's interior, photons streaming from the surface. This stability is not stasis. Inside, the star is dynamic, active, turbulent. In the core, fusion runs continuously. Protons tunnel through barriers, nuclei merge. Helium accumulates like ash in a fireplace. In the radiative zones surrounding the core, photons random walk outward, scattering billions of times. In the outer convective zone, hot plasma rises, cools and sinks in vast circulating currents, cells larger than Earth moving at meters per second. On the surface, magnetic fields create sunspots and flares, and coronal mass ejections. The star is alive with activity, though alive is a metaphor. Stars are not living things in any biological sense. But from a distance, observing over human timescales, the star appears unchanging, constant, eternal. This stability, this constancy is what makes life possible. Life needs energy, but it also needs stable, predictable energy. It needs conditions that change slowly enough for evolution to adapt. If the sun varied dramatically in output, if it brightened by a factor of 2 for a few thousand years, then dimmed again, Earth would swing between extreme climates. Oceans might boil, then freeze. Life would struggle to survive such swings, let alone develop intelligence. But the sun is stable, remarkably stable. Over the past billion years, the sun's luminosity has increased by perhaps 10%. That's a slow change, a gradual drift, slow enough for Earth's climate system and life to adapt through changes in greenhouse gases and albedo and biological processes. Over human timescales, over historical timescales, the sun is essentially constant. Year-to-year variation is less than 0.1%. The solar cycle, the 11-year cycle of sunspot activity, changes the sun's output by about 0.1% peak to trough. Barely detectable. This stability is why we're here, why life had time to evolve from bacteria to humans across nearly 4 billion years. Stars provide that stability. They're reliable, they're patient, they burn steadily for eons. But the stability is not permanent. It's not eternal. Deep inside, invisible from outside, a slow transformation is underway. The core is changing. The hydrogen is being consumed. The helium is accumulating. Slowly, imperceptibly, slowly by human standards over millions and billions of years, the core becomes richer in helium and poorer in hydrogen. The composition changes. The mean molecular weight increases because helium atoms are 4 times more massive than hydrogen atoms. The core becomes slightly denser for a given pressure and temperature. It contracts slightly, it heats slightly. The fusion rate increases. The star becomes slightly more luminous. For the sun, this effect is measurable over geological time. The sun is about 30% brighter now than when it formed 4.5 billion years ago. This creates the faint young sun paradox in Earth science. The early Earth received about 30% less sunlight than today, yet geological evidence shows it had liquid water and possibly even warm climates. How? The answer involves greenhouse gases. Earth's early atmosphere probably had much more CO2 and CH4, trapping more heat, compensating for the dimmer sun. The star doesn't notice these gradual changes. There's no consciousness, no awareness. But physically, the star is slowly evolving even during the stable main sequence. And eventually, inevitably, after billions of years of steady fusion, the hydrogen in the core will run out. Not all at once, not suddenly, but gradually, zone by zone, as the central regions are depleted first. When the very center runs out of hydrogen, fusion there stops. That region becomes pure helium, inert, unable to generate energy. But fusion continues in a shell around the helium core, in a spherical shell where hydrogen still remains, and conditions are still hot enough for fusion. And this changes everything. This marks the end of the main sequence and the beginning of something new. The star begins to evolve off the main sequence. Its billions of years of stability are coming to an end. A new chapter begins, the chapter of red giants, planetary nebulae, white dwarfs, or for massive stars, the chapter leading to supernova and neutron stars or black holes. The story continues, but the nature of the story changes dramatically. When a star exhausts the hydrogen in its core, when the last fusion reactions there sputter and die, fusion in the core stops. The nuclear fires go out. The energy source that has supported the star against gravity for billions of years disappears. There's still hydrogen in the outer layers. Plenty of it, perhaps half the star's mass or more. But the core, the central region where temperature and pressure are high enough for efficient fusion, is now almost pure helium. Perhaps 98 or 99% helium, with traces of heavier elements. And helium doesn't fuse at 15 million degrees. It requires much higher temperatures, around 100 million degrees or more, because helium nuclei have twice the charge of hydrogen nuclei and repel each other 4 times more strongly. Without fusion in the core, there's no energy generation there, no radiation pressure, no thermal pressure from fresh energy input. Gravity, held at bay for billions of years, finally gains the upper hand. The core begins to contract. As it contracts, something interesting happens that might seem counterintuitive. According to the virial theorem, a fundamental result in physics for gravitationally bound systems, when a self-gravitating gas cloud contracts and releases gravitational potential energy, about half that energy goes into heating the gas. So even though the core is losing energy overall, radiating it away to the surrounding layers and eventually to space, it gets hotter, not cooler. The temperature rises 20 million degrees, 30 million, 50 million, 80 million. And this has 2 important effects. First, the contracting. Heating core heats the layers just outside it, the shell of hydrogen-rich materials surrounding the helium core. This shell becomes hot enough for hydrogen fusion. 15 million degrees, 20 million, enough for efficient fusion via the CNO cycle. Shell burning begins. The star develops a hydrogen-fusing shell around an inert helium core. Second, the shell produces energy. Lots of energy. Often more energy than the core was producing during the main sequence, because the shell is hotter and the CNO cycle is more temperature-sensitive than the PP chain. This energy heats the overlying envelope of the star. The outer layers absorb energy from the shell and expand. The star swells. The radius increases dramatically, 10 times, 50 times, 100 times, sometimes even more. The surface moves outward, farther from the center, farther from the energy source. And as it moves outward, as the radius increases, the surface temperature drops. Why? Because of the Stefan Boltzmann law. Luminosity equals surface area times temperature to the 4th power. If luminosity increases from vigorous shell burning, but surface area increases even more from the expansion, temperature must decrease to maintain the balance. The surface cools. From 5,800 Kelvin for a sun-like star to perhaps 3,500 or 3,000 Kelvin. The color changes from yellow-white to orange to deep red. The star becomes a red giant. This is one of the most dramatic transformations in stellar evolution. A compact, stable main sequence star, perhaps 1 million kilometers in diameter like the Sun, swells to perhaps 100 million kilometers, comparable to the orbit of Mercury or Venus. Our Sun will do this in about 5 billion years. It will expand to perhaps 100 times its current radius, possibly more. Its surface will move outward past Mercury's orbit, engulfing and vaporizing the innermost planet. It will probably reach Venus. Venus will likely be engulfed as well, spiraling inward through the tenuous outer atmosphere of the red giant Sun, experiencing drag, losing orbital energy, eventually falling into denser layers and vaporizing. Earth's fate is less certain. Some models suggest Earth will be engulfed. Others suggest Earth's orbit will expand outward as the Sun loses mass through stellar winds, staying just ahead of the expanding surface. But even if Earth avoids being literally swallowed, it will be utterly destroyed as a world. The temperature will rise to hundreds or thousands of degrees. The oceans will boil away completely, water molecules dissociating and hydrogen escaping to space. The atmosphere will be stripped by the solar wind and radiation. The surface will be molten or vaporized. Life will be impossible. Not just human life, all life, every organism, every bacterium. The planet will be sterilized, reduced to a barren ball of rock, perhaps eventually vaporized entirely. But the core of the Sun, meanwhile, continues its own evolution. Still contracting, still heating, still approaching the threshold for a new kind of fusion. The helium core grows more massive as helium from the shell rains down onto it, more massive and denser and hotter. Eventually, after perhaps 100 million years of shell burning, the core reaches the critical point. About 100 million solar masses of helium, density of about 100,000 grams per cubic centimeter, temperature approaching 100 million degrees Kelvin. And then something extraordinary happens. Helium fusion ignites. In stars like the Sun, this happens in a dramatic event called the helium flash, where the entire core ignites almost explosively in a matter of seconds due to electron degeneracy effects. In more massive stars, helium ignition is more gradual, but either way, helium fusion begins. The triple alpha process. 2 helium nuclei fuse briefly into unstable beryllium-8. Before it decays, a third helium collides and fuses, forming carbon-12. Sometimes a fourth helium adds on, forming oxygen-16. Carbon and oxygen, the 2 primary products of helium fusion, the elements essential for life. Carbon for organic chemistry, oxygen for water and respiration. Both made in the cores of dying stars, both forged from helium in the final chapters of stellar evolution. The star now has a new lease on life, though a brief one. Helium fusion in the core, hydrogen fusion in a shell around it. For a Sun-like star, helium fusion lasts perhaps 100 million years, a brief coda after 10 billion years on the main sequence. Just 1% of the total lifetime. And during this time, the star is unstable. It pulsates. It sheds mass through stellar winds. The outer layers are barely bound. The escape velocity at the surface is low. Stellar winds, driven by radiation pressure on dust grains that condense in the cool outer atmosphere, blow material into space. Over millions of years, the star can lose 20 or 30% of its mass, maybe more. This material forms a slowly expanding shell around the star, eventually visible as a planetary nebula when the core is exposed, and its ultraviolet radiation ionizes the gas. Eventually, the helium runs out, all converted to carbon and oxygen. The core, now made of carbon and oxygen, contracts again. But for a star like the Sun, this is the end of the road. The core can't get hot enough to fuse carbon. That requires 600 million degrees or more. Electron degeneracy pressure halts the contraction. The core stabilizes as a white dwarf, supported by quantum mechanics. The outer layers drift away, forming a beautiful planetary nebula. The Ring Nebula, the Helix Nebula, the Cat's Eye Nebula, and thousands of others. The star is dead, but its atoms live on, scattered into space, enriching the interstellar medium with carbon, nitrogen, oxygen, and other elements forged during its life. For massive stars, the story is different. More violent, more spectacular. When they exhaust helium, their cores are massive enough to continue. Carbon fusion at 600 million degrees, neon fusion at 1.5 billion degrees, oxygen fusion at 2 billion degrees, silicon fusion at 3 billion degrees, each stage shorter than the last. Carbon burning for 1,000 years, neon for a year, oxygen for months, silicon for a day. The star becomes layered like an onion, shells of different elements burning at different temperatures. Hydrogen in the outermost shell, helium below, carbon, neon, oxygen, silicon, and at the very center, iron. Iron 56 and iron 54 and nickel 56, the most stable nuclei, the bottom of the binding energy curve. You cannot extract energy by fusing iron. Iron is the end point. Fusing iron into heavier elements costs energy, consumes it, is endothermic. When the core becomes iron, fusion as an energy source stops. The nuclear fires die, and the core, perhaps 1.5 solar masses, collapses. Not slowly, not over millions of years. In about 1 second, from Earth-sized to city-sized, from 10,000 kilometers diameter to 20 kilometers. The density becomes incomprehensible. Nuclear density. Neutron star density, 500 million tons per cubic centimeter. A teaspoon weighs as much as a mountain range. The collapse releases tremendous energy. Most escapes as neutrinos, perhaps 10 to the power of 58 neutrinos, carrying 99% of the energy. But 1% goes into the outer layers, and 1% is enough. The shockwave tears through the star at thousands of kilometers per second. The temperature spikes to billions of degrees. Nuclei are ripped apart and reassembled. Rapid neutron capture creates elements heavier than iron. Gold, platinum, uranium, all the heavy elements. And the star explodes. A supernova. For a few weeks, one dying star can outshine an entire galaxy of hundreds of billions of stars. Brighter than 100 billion suns combined, visible across millions of light years. In 1987, astronomers witnessed supernova 1987A in the Large Magellanic Cloud, 168,000 light-years away. Visible to the naked eye from the southern hemisphere, they detected the neutrinos hours before the visible light, exactly as theory predicted. 24 neutrinos in detectors around the world, messengers from the collapsing core. They watched the light curve, matching theory almost perfectly. They saw the expanding debris slam into rings of material ejected earlier, lighting them up like cosmic neon signs. And they're still watching today, nearly 40 years later. This is not destruction. This is creation. Every element heavier than iron in your body came from events like this. From supernovae, from neutron star collisions, from cosmic violence, the gold in jewelry, the platinum in catalytic converters, the iodine in your thyroid, the uranium in nuclear reactors, all forged in seconds in the fury of stellar death, all scattered across light years, all eventually incorporated into new clouds, new stars, new planets, the cycle of stellar life and death. Birth from clouds, life fusing elements, death scattering them, new birth from enriched material. The wheel turns. The universe builds complexity. Generation after generation of stars, each one slightly richer in heavy elements than the last. The first stars were pure hydrogen and helium. No carbon, no oxygen, no planets. When they died, they seeded space with the first heavy elements. The second generation formed from enriched gas. They made more heavy elements. The third generation, fourth, fifth. Our sun is perhaps third or fourth or fifth generation, formed from a cloud enriched by countless previous stars, enriched enough to form rocky planets, to create Earth, to enable chemistry complex enough for life. We exist because stars died. Billions of stars over billions of years. We are made of their remnants, their ashes, their gifts to the universe. The stars are not what you think. They are not eternal. They are not simple. They are not just lights. They are machines, engines, factories, billion-year fusion reactors that convert hydrogen to helium and build the periodic table element by element. They are the forges of creation, the wombs of elements, the architects of complexity. Without them, the universe would be simple, just hydrogen and helium forever. No chemistry, no planets, no life. With them, the universe becomes interesting, rich, complex, capable of producing structure, planets, oceans, life, intelligence. They are still running, right now, across the galaxy, across the universe, some young, just ignited, some old, approaching death, some dying, some exploding, some being born. The work continues, the cycle turns, the universe evolves, and you are part of it, made of stardust, literally. Every atom in your body except hydrogen came from stars, from fusion or from supernovae. The oxygen you breathe, forged in massive stars. The carbon in your DNA, made in red giants. The calcium in your bones, from stellar nucleosynthesis. The iron in your blood, from supernova explosions. You are not separate from the cosmos. You are made of it. You are it, rearranged into a form that can think and wonder and understand. You are the universe contemplating itself. Atoms forged in stellar cores, arranged by evolution into a pattern that generates consciousness. And that is extraordinary, profound, almost miraculous, though it follows entirely from physics and chemistry and biology. Look up tonight. See the stars. Understand what they are, what they do, what they've done. They are machines, still running, still creating. The forges that made you, the engines that built the elements that make up your world. They are not eternal, but they are patient. They work on timescales that dwarf human history, human civilization, human evolution. They were here long before us. They will be here long after. The stars are still burning, and the universe is still creating. One fusion reaction at a time, one star at a time, one atom at a time. The work continues, the machines run, and you are here briefly to witness it, to understand it, to marvel at it. You are stardust, contemplating stars. And that is enough. That is everything. Pause for a moment. Let this settle. The stars are not distant, not separate, not alien. They are family, ancestors, creators. Every breath you take contains oxygen made in stars. Every heartbeat pumps iron through your veins, iron forged in a supernova explosion billions of years ago. The calcium that gives structure to your skeleton was synthesized in the core of a dying star, then scattered into space, then gathered by gravity into the cloud that formed our solar system, then incorporated into Earth, then taken up by life, then passed through food chains, and finally became part of you. That calcium atom in your bone has a history, a journey spanning billions of years and light years of space. It was hydrogen once, primordial hydrogen from the Big Bang. Then it became helium inside a star, then carbon through helium fusion, then heavier elements through further reactions, eventually calcium, forged in a supergiant's core, then scattered in a supernova. Drifting through space for millions of years, part of a vast cloud. eventually swept up in the collapse that formed the sun and planets. Incorporated into Earth's mantle, erupted in a volcano, weathered into soil, absorbed by a plant, eaten by an animal, eaten by another animal, eventually eaten by you or your ancestors. Now it's in your bone, giving it strength, allowing you to stand and move. One atom. Billions of years. A cosmic odyssey. And that's just one atom. You contain about 7 times 10 to the power of 27 atoms. 7 billion atoms. Each with its own history. Each forged in stars or in the Big Bang. Most from stars. Most from the slow, patient work of stellar nucleosynthesis, or the violent fury of supernovae, or the exotic conditions in neutron star mergers. You are an assembly of stellar products, a collection of atoms that have cycled through the universe for eons before coming together temporarily as you. This is not metaphor. This is not poetry. This is literal truth. You are made of stars, and the stars are still working, still fusing, still creating. Right now, at this moment, as you read these words, somewhere in the Milky Way, a star is being born. In a molecular cloud, a dense core has collapsed past the point of no return. The temperature at the center has reached 10 million degrees. The first fusion reactions have ignited. A new star joins the galaxy. A new fusion reactor begins its billion-year task. It will burn steadily, perhaps for trillions of years if it's a red dwarf. Perhaps for only millions if it's massive. But for its entire life, it will convert hydrogen to helium, mass to energy, contributing to the cosmic work of building complexity. Right now, another star is dying. A red giant, perhaps in the constellations Cygnus or Sagittarius, has exhausted its helium. Its core has contracted to a white dwarf. Its outer layers are drifting away at tens of kilometers per second, forming a planetary nebula that will glow for thousands of years before dispersing. The atoms in those outer layers, carbon, nitrogen, oxygen, neon, all forged in the star's core during its life, are joining the interstellar medium, enriching the galaxy, providing raw material for future stars, future planets, perhaps future life. Right now, somewhere in a distant galaxy, a massive star is in its final day. Its iron core has grown to 1.5 solar masses. It's on the edge of collapse. Perhaps it's already collapsed, and the light from the supernova is streaming through space toward us, though it won't arrive for millions of years. When it explodes, it will briefly outshine its entire galaxy. It will create a neutron star or black hole. It will scatter heavy elements across hundreds of light years. It will trigger new star formation in nearby clouds with its shockwave. The cycle continues. Birth, life, death, rebirth. Stars forming from the ashes of previous stars. Each generation slightly richer in heavy elements. Each generation capable of forming more complex chemistry. The universe is still young. Only 13.8 billion years old. That sounds ancient by human standards, but it's young cosmologically. Star formation is still vigorous in many galaxies. The Milky Way forms perhaps 1 or 2 new stars per year on average. Some galaxies form hundreds per year. Most of the stars that will ever exist have not yet been born. Most of the planets have not yet formed. Most of the possible life has not yet emerged. We live early in cosmic history. The age of stars has barely begun. Think about timescales. Really think about them. The universe is 13.8 billion years old. That's the age of everything: space, time, matter, energy, all of it. The first stars formed perhaps 100 or 200 million years after the Big Bang, when the universe was about 1 to 2% of its current age. Just starting. The Sun and Earth formed 4.5 billion years ago, when the universe was about 33% of its current age. relatively recent in cosmic terms, life on Earth emerged perhaps 3.8 to 4 billion years ago, almost immediately after Earth cooled enough to have liquid water. Very soon after planet formation, complex life, multicellular organisms, animals, plants, emerged only about 600 million years ago in the Cambrian explosion. Very recently, humans, our species, Homo sapiens, emerged about 300,000 years ago. Extremely recently, an eye blink, civilization, agriculture, cities, writing, only about 10,000 years ago, less than an eye blink, essentially now. Modern science, our understanding of stars and fusion and elements, only about 100 years old. The understanding you've gained reading this developed mainly in the last century. We've understood what stars are for less than 100 years, less than 1/10,000,000th of the universe's age. For 99.999999% of cosmic history, no one knew what stars were. Now we do. Now you do. And the universe still has a long future ahead. The sun will burn for another 5 billion years. That's more time than Earth has existed so far. More time than life has existed. Plenty of time for evolution, for change, for the unforeseeable. Red dwarfs will burn for trillions of years. Trillions. Hundreds or thousands of times longer than the universe has existed so far. The last stars won't die for tens of trillions of years. 10 trillion. A number hard to comprehend. If you compressed the entire history of the universe so far, all 13.8 billion years, into a single 24-hour day, the age of stars would last for more than 20,000 years at that scale. We are very, very early. The universe is young, the story is just beginning. And yet, despite being early, despite living in a universe that's barely started its stellar age, we can understand it. We can look up at stars and know what they are, what powers them, how they work, how they live and die. We can calculate their temperatures from their colors, their masses from their motions in binary systems, their compositions from their spectra. We can model their interiors with computers, solving the equations of stellar structure, predicting how they'll evolve. We can watch them explode in supernovae and see our predictions confirmed in real time. We understand fusion. We know the cross-sections. We know the reaction rates. We can calculate how fast hydrogen converts to helium at 15 million degrees. We've even created fusion ourselves briefly in laboratories and weapons. We've replicated on a tiny scale what stars do naturally. We've sent spacecraft to study the sun up close. Parker Solar Probe skims through the corona at temperatures of millions of degrees, collecting data, answering questions. We've built telescopes that can see in every part of the spectrum: radio, microwave, infrared, visible, ultraviolet, X-ray, gamma ray, each revealing different aspects of stellar behavior. We've discovered thousands of planets around other stars, confirming that solar systems are common, that stars often have planets. We've found molecules in space, organic molecules, complex chemistry, the building blocks of life, showing that the universe is rich in chemistry, capable of complexity. We are not separate from nature, studying it from outside. We are nature studying itself, the universe examining its own workings through human consciousness. Atoms arranged by evolution into patterns that can think, understand, wonder. Carbon-based life contemplating carbon-based chemistry. Star-forged elements understanding star-forged elements. This is extraordinary, profound, almost miraculous, though it follows entirely from natural law. The universe is not designed for us. It's indifferent to our existence, but it's capable of producing us, and that's remarkable enough. We exist in the narrow window where stars still burn, where planets can form, where chemistry is complex enough for life, where stable energy sources allow evolution. We exist in the brief window when consciousness can emerge and contemplate its origins. This window won't last forever. Trillions of years from now, the universe will be dark. Stars will have exhausted their fuel. Chemistry will be frozen out. Life will be impossible, but now, in this era, in this cosmic moment, we're here, and we can understand. We can look up and see not just lights, but fusion reactors. Not just stars, but machines billions of years old. We can trace our own atoms back through stellar evolution, back through supernovae, back through the cosmic cycles of death and birth. We can know our place in the universe, our origins, our composition, our history. We are stardust. And knowing that, really knowing it, understanding it deeply, changes how you see everything. The night sky is full of stories. Not the ancient stories of heroes and gods, though those are beautiful in their way, but real stories, physical stories, histories written in light. That star there, Betelgeuse, the red supergiant in Orion's shoulder. It's dying. Its core is filling with iron. It could explode as a supernova tomorrow or 100,000 years from now. When it does, it will be bright enough to cast shadows at night, visible during the day, as bright as the full moon. And we'll see it happen. We'll watch a star die in real time. Well, not real time. The light will take 550 years to reach us, so it will have already happened centuries before we see it. But we'll witness it. That star there, Sirius, the brightest star in the night sky. It's actually a binary system. Sirius A is a white main sequence star, twice the Sun's mass, burning hotter and faster. Sirius B is a white dwarf, the remnant of a star that already died, now just a dense ember slowly cooling. They orbit each other every 50 years, bound by gravity, dancing through space together. That cluster there, the Pleiades, the Seven Sisters. Those are young stars, only about 100 million years old. They formed together from the same cloud. They're still gravitationally bound, traveling through the galaxy together. In a few 100 million years, they'll drift apart, scattered by gravitational interactions with other stars. But for now, they're a family, newborns by stellar standards. That galaxy there, Andromeda, barely visible to the naked eye. It contains 1 trillion stars. 1 trillion. Each one a fusion reactor, each one converting hydrogen to helium, and it's moving toward us at about 110 kilometers per second. In about 4 billion years, it will collide with the Milky Way. The galaxies will merge, stars passing by each other, very few actually colliding because stars are so small compared to the distances between them. The sky will be spectacular. Andromeda will grow larger and larger over millions of years, eventually filling the sky, then merging with the Milky Way's disk, creating chaos, triggering bursts of star formation. By then, the sun will be a red giant. Earth will be dead. But the collision will be beautiful, a cosmic dance visible to any observers that remain or emerge. Every light in the sky has a story, a history, a future. The universe is not static, it's dynamic, evolving, changing on timescales from seconds to trillions of years. And we're here to witness it, to understand it, to appreciate it. So tonight, if you can, go outside. Wait for darkness. Find a place away from city lights if possible. Let your eyes adapt. Wait 15 or 20 minutes. Don't look at your phone or any bright lights. And then look up. Really look. Not just glancing, but observing, studying, contemplating. What you're seeing is profound. Every point of light is a star, a fusion reactor, a machine converting mass to energy, hydrogen to helium, and beyond. Some are larger than the sun, some smaller, some younger, some older. Some are in the prime of life, stable, steadily fusing. Some are dying, swelling into giants, shedding their outer layers. Some are already dead, their light traveling for years or centuries, showing us what they were, not what they are. You're looking backward in time. The light from Alpha Centauri is 4.3 years old. From Vega, 25 years. From Deneb, about 1,500 years old. That light left when the Western Roman Empire was collapsing and the Dark Ages were beginning in Europe. You're seeing the past, the universe as it was, not as it is. And you're seeing the machinery of creation, the forges that made the atoms in your body. You are made of stars. Every atom except the primordial hydrogen came from stellar nucleosynthesis or supernovae. The oxygen you breathe with every breath, the carbon that forms the backbone of every molecule in your body, the nitrogen in your DNA and proteins, the calcium in your bones, the iron in your hemoglobin, carrying oxygen through your blood, the phosphorus in ATP, the energy currency of your cells, the sulfur in some of your amino acids, the trace elements zinc, copper, iodine, selenium, all forged in stars or supernovae. All of it came from stellar furnaces. All of it was created through fusion or supernova nucleosynthesis. All of it was scattered into space when stars died. All of it was gathered by gravity into new clouds, new stars, new planets. All of it eventually became you. You are stardust, contemplating stars. And the stars are still working, still fusing, still creating. The cycle continues. The work never stops. Stars are being born right now. Stars are dying right now. The universe is still building complexity, still enriching itself with heavy elements, still evolving. And you are part of this process, not separate from it, not outside it, part of it. You are the universe examining itself. Atoms arranged by evolution into a pattern that generates consciousness, that can think and wonder and understand. Carbon contemplating carbon. Star-forged elements understanding star-forged elements. This is the gift of science. Not just knowledge, but perspective. Understanding your place in the cosmos. You are small, yes. Brief, yes. Temporary, yes. But you are also magnificent, connected to everything, made of stars, and you can understand it. That understanding, that knowledge, that perspective, that's precious. That's remarkable. Billions of years of cosmic evolution led to you. Countless stars lived and died to create the elements you're made of. Billions of years of biological evolution shaped you into a being capable of understanding. And now, you know. You understand. You know what stars are, what they do, how they work. You know you're made of their products. You know your place in the cosmic story. That knowledge changes you. It should change you. When you look up at the stars now, you don't just see lights. You see machines, forgers, creators. You see your origins, your ancestors, your makers. The stars are not what you thought. They are more. They are billion-year fusion reactors, self-regulating engines of nucleosynthesis, architects of complexity, forgers of the elements. They are the machines that built the universe we inhabit, the chemistry we're made of, the complexity that makes life possible. They are still running, still working, still creating, and you are made of their gifts. Look up, wonder, understand. The stars are burning. The work continues, and you are here to witness it. You are stardust, awakened, and that is everything. Thank you for taking this journey with us, for having the patience to sit and contemplate deep time, vast scales, cosmic processes that dwarf human experience, for opening your mind to the strangeness and beauty of the universe as it actually is, not as intuition suggests it should be. The stars are not what you thought when we began, Perhaps they're more remarkable than you imagined, more complex, more important, more connected to you personally. You cannot look at the night sky the same way now. You cannot see starlight without knowing it comes from fusion, from the conversion of mass to energy in cores heated to millions of degrees. You cannot think about your own body without realizing every atom has a cosmic history, a journey through stars and space and time. This is the power of understanding, of knowledge, of science. It transforms the ordinary into the extraordinary. It reveals the hidden connections between you and the cosmos. It shows you that you belong here, that you're part of this, that you're made of the universe itself. The stars are still burning. Somewhere right now, a star is fusing its 4 billionth ton of hydrogen today. Tomorrow, it will fuse 4 billion tons more. And the next day, and every day for billions of years. Patient, persistent, inexorable, building the elements, creating complexity, making the universe interesting. And we are here briefly to witness it, to understand it, to marvel at it. The billion-year machines are still running, and you are made of their work. Look up tonight, see the machines, know yourself,